So, here's something worth sitting with for a moment. Right now, tonight, as you're lying there getting comfortable, the deepest parts of the ocean are in complete darkness. Not the kind of darkness you get when you turn off the lights in your bedroom, where your eyes eventually adjust and you can make out the outline of the dresser or the faint glow of a charger cable. No. This is a darkness so total, so absolute, that if you spent 1,000 years down there, your eyes would never adjust, because there is simply no light to adjust to. Not a single photon of sunlight reaches the bottom of the Mariana Trench. And in that darkness, right this very second, there are creatures moving, feeding, reproducing, living entire lives in a world we have mapped less thoroughly than the surface of Mars. Think about that. We have better maps of a planet 55 million kilometers away than we do of the floor beneath our own ocean. And that's really where this story begins, with the fact that we live on a water planet and we barely know what's down there. About 71% of Earth's surface is covered by ocean. You've probably heard that number before, but let it settle in. Nearly 3/4 of the world you live on is underwater, and the average depth of all that water is about 3,700 meters. That's over 2 miles straight down. Most of the ocean floor has never been seen by human eyes, never been touched by human hands, never been recorded by any instrument at all. The best estimates suggest we've explored somewhere around 5 to maybe 20% of it, depending on what you count as explored. And even that generous upper number mostly means we've bounced sonar off it from the surface. Actually going down there, actually looking, that number drops to something almost embarrassingly small. So let's talk about what's actually down there, and why it's so strange, and why the story of how we figured out even the little bit we know is one of the most fascinating engineering stories nobody tells. The first thing you need to understand is pressure. It's the single most important fact about the deep ocean, and it governs everything. What can survive down there, what we can build to go down there, and why it took us so absurdly long to even try. Here at the surface, you're living under 1 atmosphere of pressure. That's the weight of all the air above you, pressing down, about 14.7 pounds per square inch. You don't notice it because your body is perfectly adapted to it. Your internal pressure pushes back and everything balances out. But water is roughly 800 times denser than air. So when you go underwater, the pressure increases fast. For every 10 meters you descend, you add another full atmosphere. At 10 meters down, you're at 2 atmospheres. At 100 meters, 11 atmospheres. At 1,000 meters, you're at about 101 atmospheres. And at the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure is over 1,000 atmospheres. That's roughly 15,700 pounds pressing on every single square inch. Imagine taking a 1-inch square on your thumbnail and stacking 8 or 9 pickup trucks on it. That's what the water is doing to everything at that depth, from every direction, constantly. Now here's what that means in practical terms. If you took a styrofoam cup, and actually, deep-sea researchers do this as a kind of tradition, and you attached it to the outside of a submersible heading to the deep ocean by the time it came back up, that cup would be about the size of a thimble. The air pockets in the styrofoam get crushed to almost nothing. The cup is structurally intact. It's just been compressed into this dense little miniature version of itself. Researchers write messages on them before they go down, or their kids draw pictures on them, and they come back as these tiny, perfect little souvenirs of impossible pressure. It's charming, but it also tells you something terrifying about what that environment does to anything with empty space inside it. And you, by the way, are full of empty spaces. Your lungs, your sinuses, your ears, your gut. The deep ocean would not be kind to you. The ancient world had almost no concept of any of this. For most of human history, the ocean was a surface to travel across, a source of food you could pull from the shallows, and a mystery everywhere else. The Greeks and the Romans knew the Mediterranean was deep in places, but they had no way to measure how deep. Aristotle wrote about marine life, and he was actually a surprisingly careful observer. He described the anatomy of octopuses with an accuracy that wouldn't be matched for nearly 2,000 years. But even Aristotle thought of the deep sea as essentially lifeless, a dark wasteland beneath the productive, sunlit waters near shore. And honestly, that assumption stuck around for an astonishingly long time. The first real attempts to measure ocean depth were almost comically simple. You took a long rope, tied a heavy weight to the end, and threw it overboard. When the weight hit bottom, you measured how much rope you'd let out. This is called sounding, and it's where the phrase, sounding the depths, comes from. The problem is that it only works in relatively shallow water. Once you're trying to sound depths of 1,000 meters or more, the rope itself becomes a problem. It's heavy. It drifts in currents. It's hard to tell when the weight has actually hit bottom versus when the rope is just piling up on itself or being dragged sideways. Early attempts at deep ocean sounding produced wildly inconsistent results. Sailors would get readings that varied by hundreds or even thousands of meters in the same location, and nobody could tell which ones were right. But people kept trying, because by the early 19th century, there were real practical reasons to know what the ocean floor looked like. The telegraph was coming, and this is one of those moments where engineering need and scientific curiosity collide in the most productive possible way. The idea of laying a telegraph cable across the Atlantic Ocean, connecting Europe and North America with an electrical wire running along the seafloor, was one of the most ambitious engineering projects anyone had ever proposed. And to do it, you needed to know what was down there. Was the bottom flat? Was it rocky? Were there underwater mountains that would snag the cable? How deep was the deepest part? Nobody knew. The person who probably did more than anyone else to answer these questions in the mid-1800s was Matthew Fontaine Maury, an American naval officer who became the first superintendent of the United States Naval Observatory. Maury was a fascinating character. He'd been a promising young naval officer, but a stagecoach accident in 1839 badly injured his leg and ended his sea career. So he turned to data. He started systematically collecting logbooks from Navy ships, thousands of them, and compiling information about winds, currents, and ocean depths. He was essentially doing big data analysis 150 years before anyone called it that, and he became obsessed with the question of the ocean floor. He organized some of the first systematic deep-sea sounding expeditions using improved techniques with detachable weights, so the line would go slack the moment the weight hit bottom, giving you a more reliable depth reading. In 1855, Maury published a bathymetric map of the North Atlantic, one of the first real maps of the deep ocean floor. And it showed something nobody had expected. The middle of the Atlantic wasn't just a flat, featureless plain. There was a ridge there, a massive underwater mountain range running roughly north to south down the center of the ocean. Maury called it Telegraph Plateau because the relatively shallow, flat area on top of it seemed like the perfect place to lay a cable. He didn't fully understand what he'd found. The theory of plate tectonics was still over a century away. But he'd glimpsed one of the largest geological features on Earth, the Mid-Atlantic Ridge, which we now know stretches over 16,000 kilometers and is part of a global system of underwater mountain ranges where new oceanic crust is being born as tectonic plates pull apart. And here's the thing. Even with Maury's maps, laying that transatlantic cable was a nightmare. The first serious attempt came in 1857 and 1858, funded largely by the American businessman Cyrus Field, who had essentially bet his entire fortune on the idea. The cable was manufactured in England, loaded onto two ships, the HMS Agamemnon and the USS Niagara, and they sailed to the middle of the Atlantic to splice their halves together and then steam in opposite directions, one toward Ireland and one toward Newfoundland, paying out cable as they went. The first attempt in 1857 failed when the cable snapped after about 335 miles. They tried again in 1858, and after multiple breaks, violent storms that nearly sank the Agamemnon, and what must have been absolutely unbearable tension, they actually succeeded. On August 16, 1858, Queen Victoria sent a message to President James Buchanan through the cable. It took over 17 hours to transmit a message of about 100 words because the signal was so faint, but it worked. There were celebrations in the streets. New York City held a parade so enthusiastic that fireworks set the roof of City Hall on fire. And then, 3 weeks later, the cable died. The signal just faded away to nothing. The insulation had failed. The gutta percha, a natural rubber-like material they'd used to coat the copper wire, had degraded and seawater had gotten in, and that was that. Millions of dollars, years of effort, multiple near disasters at sea, and the whole thing lasted less than a month. Some people accused Cyrus Field of fraud. Some said the whole thing had been a hoax and the messages were faked. Field was financially ruined and publicly humiliated. But here's what's wild. He didn't give up. It took 8 more years, a civil war, and a complete redesign of the cable. But in 1866, using the Great Eastern, the largest ship in the world at the time, an absolute monster of Victorian engineering, they laid a new cable that actually worked. And this time, it stayed working. And that cable, running along the bottom of the Atlantic in total darkness under crushing pressure, connected the old world and the new world in something close to real time for the first time in human history. Now, the reason I'm telling you all this is that the telegraph cable story reveals something important about the deep ocean. Every time engineers tried to work down there, the ocean pushed back. The pressure, the cold, the corrosive salt water, the sheer logistical impossibility of working in a place you couldn't see or reach, it humbled everyone who tried. And the scientific community was just as humbled. Because even as they were laying cables and taking soundings, a major scientific debate was raging about whether anything could even live in the deep ocean at all. The dominant theory for much of the 19th century was something called the Azoic hypothesis. It was championed by Edward Forbes, a British naturalist who had done extensive dredging in the Aegean Sea in the early 1840s. Forbes noticed that as he dredged deeper, he found fewer and fewer organisms. He extrapolated from this, reasonably enough it seemed at the time, that below about 300 fathoms, roughly 550 meters, the ocean was essentially lifeless. An azoic zone. No light, no food, crushing pressure, near freezing temperatures. Nothing could possibly live there. And for about 20 years, this was the scientific consensus. The deep ocean was dead, a vast, dark, empty desert of water and mud. It was a perfectly logical conclusion based on the available evidence. The problem was that the available evidence was terrible. Forbes's dredges were small, crude, and often came up empty, not because there was nothing down there, but because they weren't very good at catching things. It's a bit like dragging a butterfly net through a football stadium at night and concluding that the stadium is empty because you didn't catch anything. The azoic hypothesis started to crumble in the 1860s, and the way it crumbled is one of those beautiful moments in the history of science where reality just refuses to cooperate with a tidy theory. When they pulled up those transatlantic telegraph cables for repair, the cables were encrusted with living organisms, animals that had attached themselves to the wire at depths well below Forbes's supposed lifeless zone. There were corals, there were mollusks, there were all sorts of creatures happily living in a place that science had declared uninhabitable. And around the same time, other naturalists were doing deeper dredges with better equipment and pulling up specimens from 1,000 meters, 1,500 meters, 2,000 meters down. The deep ocean wasn't dead at all. It was alive in ways nobody had imagined, and the sheer variety of what was coming up in those nets was staggering. Creatures with no eyes, because why would you need eyes in permanent darkness? Creatures with enormous eyes, because even the faintest bioluminescent glow becomes worth detecting when it's the only light you'll ever see. Animals that were ghostly pale, translucent, almost spectral, because pigmentation costs energy, and there's no camouflage advantage when nobody can see color. And then there were the ones that were jet black or deep crimson red. And here's a neat trick of physics for you. Red light is the first wavelength to be absorbed as you go deeper in water. By the time you're a few hundred meters down, red light simply doesn't exist anymore. So a deep red animal in the deep ocean is effectively invisible. It's wearing the perfect camouflage, and it didn't need to be blue or transparent to achieve it. Just red. Nature figured that out long before we understood the physics behind it. So by the late 1860s, the scientific community was buzzing. Forbes's azoic hypothesis was in tatters, and the big question had flipped entirely. It wasn't, is there life in the deep ocean, anymore. It was, what on earth is down there, and how much of it is there? And this is where one of the most ambitious scientific expeditions in history enters the picture. The voyage of HMS Challenger. Now, the Challenger expedition is one of those stories that deserves to be as famous as the voyages of Darwin on the Beagle or Cook's circumnavigations, but somehow it doesn't get the same popular attention. Which is a shame, because what this ship and its crew accomplished between 1872 and 1876 essentially created the science of oceanography. Before Challenger, studying the deep ocean was a scattered ad hoc affair. A few dredges here, some temperature readings there, individual naturalists doing what they could with limited resources. After Challenger, it was a discipline. The driving force behind the expedition was a Scottish naturalist named Charles Wyville Thomson. Thomson had been one of the people doing those deeper dredges in the late 1860s, working with a colleague named William Benjamin Carpenter. They'd convinced the Royal Navy to lend them ships for short cruises. First HMS Lightning in 1868, then HMS Porcupine in 1869 and 1870. And what they found was electrifying. Life at great depths, yes, but also something else. They discovered that the deep ocean wasn't uniformly cold, as everyone assumed. They found pockets of warm water and cold water sitting right next to each other at depth, separated by what we'd now call submarine ridges. The ocean floor had topography, had structure, had features that influenced how water moved. This was huge, and it convinced Thomson and Carpenter that a much larger, more systematic expedition was needed. They lobbied the Royal Society. The Royal Society lobbied the Admiralty. And remarkably, the British government agreed. They took a naval corvette, HMS Challenger, a three-masted, square-rigged warship with auxiliary steam power, stripped out most of her guns and converted her into a floating laboratory. They installed dredging equipment, specimen storage, chemical analysis stations, sounding gear. They loaded her with miles of rope, hundreds of thermometers, sampling bottles, trawl nets, and enough preserving alcohol to keep specimens intact for years. The scientific team was led by Thomson himself and included a young naturalist named John Murray, who would go on to become one of the founding figures of marine science. Challenger left Portsmouth on December 21st, 1872, and over the next 3.5 years, she sailed nearly 70,000 nautical miles, crossing the Atlantic, the Pacific, the Indian Ocean, and even pushing south toward the Antarctic ice. The crew made 362 observation stations, points where they'd stop the ship, take depth soundings, measure water temperature at various depths, collect water samples, and dredge or trawl the bottom. Think about what that means in practical terms. At each station, they'd have to lower sounding equipment thousands of meters on hemp rope, wait, haul it back up, lower thermometers, lower water sampling bottles, lower dredges, haul everything back up by hand or with steam winches, process and preserve whatever came up, record everything, and then sail to the next station and do it all again, in every kind of weather, in every ocean on the planet, for 3.5 years. The crew, it has to be said, were not always thrilled about this. Most of them were Royal Navy sailors who'd signed up for what they thought would be a normal naval cruise. Instead, they found themselves spending hours hauling mud up from the bottom of the ocean in the middle of nowhere, while scientists got excited about things that looked, to the average sailor, like formless blobs of jelly. Morale was a genuine problem. Something like 1/4 of the crew deserted over the course of the voyage, and several died from disease or accidents. It was grueling, unglamorous work, but the results were extraordinary. Challenger discovered over 4,700 new species. Let that sink in for a moment. 4,700 species that science had never seen before, pulled from the deep ocean over a single expedition. They found life at every depth they sampled. They mapped the ocean floor in unprecedented detail, confirming the existence of the mid-Atlantic ridge that Maury had hinted at, and revealing vast abyssal plains, underwater mountain ranges, and deep trenches. And on March 23, 1875, in the western Pacific near the Mariana Islands, they made a sounding that returned a depth of 8,184 meters, over 26,000 feet. They had found the deepest point in the ocean that anyone had yet measured. It wasn't quite the deepest point overall, as we'd later learn, but it was in the right neighborhood. That area is still called the Challenger Deep, and it remains the deepest known point on Earth's surface, measured more precisely now at about 10,935 meters, nearly 11 kilometers of water, almost 7 miles straight down. Here's what's disturbing about that number, and I mean genuinely unsettling if you sit with it for a moment. If you took Mount Everest, the tallest thing on the surface of the Earth, 8,849 meters above sea level, and dropped it into the Challenger Deep, the summit would still be more than 2,000 meters underwater. More than a mile of ocean above the tallest mountain on the planet. The deep ocean isn't just deep in a casual, oh, that's pretty far down sense. It is deep on a scale that makes our largest terrestrial landmarks look modest. And the pressure down there. We talked about pressure earlier, how it builds with depth. At the bottom of the Challenger Deep, the pressure is roughly 1,100 times atmospheric pressure at sea level. About 16,000 pounds, per square inch. Every square inch of anything you put down there is being squeezed with the force of a large car sitting on it. The water itself is actually measurably compressed at that depth. It's denser, slightly warmer than you'd expect because the compression itself generates a tiny amount of heat. If you could somehow magically remove all the pressure and let the water in the deepest trenches expand to its normal density, the global sea level would actually rise by something like 30 meters. The ocean is literally being squeezed smaller by its own weight, and there's a meaningful amount of volume locked up in that compression. The Challenger expedition returned to England in May 1876, and then came what might have been the even more heroic part, processing the results. Thomson oversaw the beginning of this work, but he was exhausted and in poor health from the voyage, and he died in 1882 before the reports were finished. John Murray took over, and over the next 19 years, he supervised the publication of the Challenger reports, which eventually ran to 50 volumes, totaling nearly 30,000 pages. It remains one of the most comprehensive scientific publications ever produced from a single expedition. Murray himself became fascinated by the sediments they'd collected from the ocean floor, and his analysis of those sediments revealed something remarkable. The deep ocean floor is carpeted with the remains of dead organisms. Billions upon billions of tiny shells from microscopic creatures called foraminifera and radiolarians, drifting down over millions of years to form a slow, steady rain of biological debris. Murray called it the rain of detritus from above. We now call it marine snow. Marine snow. That's one of those terms that sounds almost poetic until you think about what it actually is. It's a constant, gentle, never-ending fall of dead things. Bits of dead plankton, fecal pellets, shed mucus, fragments of larger organisms, bacteria clinging to tiny particles, all of it sinking slowly, through kilometers of dark water. It can take weeks for a particle of marine snow to drift from the surface to the abyssal floor. And this is essentially the only food source for most of the deep ocean. Everything down there, with a few fascinating exceptions we'll get to later, is surviving on this trickle of organic matter falling from the sunlit world above. The deep ocean is a world that runs on leftovers, on scraps, on the biological equivalent of crumbs falling from a table that's miles above your head. And yet it works. Life persists down there in staggering diversity, on this meager diet. Some of the adaptations organisms have evolved to cope with the scarcity are almost heartbreaking in their efficiency. Deep-sea fish tend to have reduced muscles, reduced bones, watery flesh. Everything about them is built to minimize energy expenditure. Some of them barely move at all, just hovering in the darkness, waiting for something edible to drift within reach. Their metabolisms are slowed to a crawl. Some deep-sea creatures can go months without eating. There's a species of deep-sea spider crab that's been observed sitting motionless in the same spot for over a year, not hibernating, not dormant, just waiting, conserving every calorie. And the deeper you go, the stranger the food strategies become. In the Hadal zone, that's the name for the deepest parts of the ocean, the trenches below 6,000 meters, named after Hades, the Greek god of the underworld. In the Hadal zone, organisms have been found that seem to derive nutrition from the sediment itself, processing vast quantities of mud to extract whatever trace organic compounds might be present. They're essentially eating dirt, very slowly, in total darkness, under pressures that would crush a submarine like a tin can. But here's what might be the most disturbing fact about the deep ocean's food web, and it connects to something much larger. The amount of marine snow that reaches the deep seafloor has been declining. As surface ocean temperatures rise due to climate change, the biological communities in the upper ocean are shifting, and in many regions, less organic material is making it down to the deep, which means the already meager food supply for the largest habitat on Earth is getting even more meager. We don't fully understand the consequences of that yet, because we barely understand the deep ocean ecosystem to begin with. We're changing something we haven't even finished discovering. That tension between the urgency of understanding the deep ocean and the sheer difficulty of getting down there to study it has driven some of the most remarkable engineering achievements in human history. Because after Challenger mapped the depths and cataloged what lived there, the next question was obvious and tantalizing and terrifying all at once. Could we actually go down there ourselves? Could a human being descend into the abyss and survive? The first serious attempt to answer that question came from an unlikely pair, a Swiss physicist and his son, and the machine they built was one of the strangest-looking vessels ever to float on water. They called it a bathyscaphe, from the Greek words for deep and ship, and it looked nothing like what you'd imagine a submarine to look like. Think of it more as an underwater balloon, and I mean that almost literally. The physicist was Auguste Piccard, and if that name sounds familiar, it might be because before he ever thought about the ocean floor, he was famous for going in the opposite direction. In 1931, Auguste Piccard became the first human being to reach the stratosphere, ascending to nearly 16,000 meters in a pressurized aluminum gondola suspended beneath a hydrogen balloon. He wanted to study cosmic rays at altitude, and he figured the best way to do it was to just go up there himself. That tells you something about the kind of person he was. When Auguste Piccard wanted to measure something, he built a machine and climbed inside it. So when he turned his attention downward, toward the ocean, he applied the same basic logic. A stratospheric balloon works because the gas inside the envelope is lighter than the surrounding atmosphere, so it rises. Piccard reasoned that you could invert this principle for the ocean. Instead of a light gas surrounded by heavier air, you'd use a light liquid surrounded by heavier water. And the light liquid he chose was gasoline. Regular aviation gasoline. It's less dense than seawater, so a large tank of gasoline would provide buoyancy. It would want to float, just like a balloon wants to rise. Beneath that float tank, you'd hang a small, incredibly strong steel sphere, the crew cabin, just like the gondola hanging beneath his stratosphere balloon. To descend, you'd flood small tanks with seawater, making the whole assembly heavier than the water around it, and down you'd go. To ascend, you'd release iron ballast, literally drop heavy pellets, and the buoyancy of all that gasoline would pull you back to the surface. Here's what's clever about the gasoline, and this is a detail that I think is just beautiful from an engineering standpoint. Gasoline is a liquid, which means it's essentially incompressible. As the bathyscaphe descends and the pressure outside increases enormously, the gasoline barely changes volume. Compare that to a gas-filled balloon, which would be crushed flat within the first few hundred meters. The gasoline just sits there, maintaining its buoyancy, indifferent to the pressure. And because the float tank isn't a sealed pressure vessel, it has openings at the bottom that let seawater press in against the gasoline. The tank walls don't have to bear the pressure differential at all. The pressure inside and outside the tank is essentially equal. The only part of the entire vehicle that has to withstand the full pressure difference is that small crew sphere, because inside it, the two occupants are breathing air at normal atmospheric pressure. Everything else is pressure equalized. So you've reduced the impossible engineering problem of building an entire large submarine to withstand crushing deep ocean pressure down to the much more manageable problem of building one small sphere to withstand it. That's the kind of insight that separates a good engineer from a great one. Piccard built his first bathyscaphe, the FNRS-2, in the late 1940s and tested it unmanned in 1948 off the coast of West Africa, near Dakar. It reached a depth of about 1,380 meters, which was promising, but the float was damaged during recovery in rough seas. The project went through some political and financial complications. The Belgian National Science Fund had sponsored it, and there were disagreements about the direction of the program. And eventually, Piccard went his own way and built an improved version. This was the Trieste, constructed in Italy, in the city of Trieste on the Adriatic coast, and completed in 1953. The crucisphere was manufactured by the Krupp Steelworks in Germany, forged from a special high-strength steel with walls about 12 centimeters thick. The interior was tiny, just barely enough room for two people to sit with their knees nearly touching, surrounded by instruments, breathing recycled air. One small porthole of thick acrylic let them look outside. Now, Auguste was getting older by this point. He was born in 1884, so he was approaching 70. And increasingly, it was his son Jacques who piloted the Trieste on its dives. Jacques Piccard had grown up watching his father build impossible machines and ride them to impossible places, and he'd absorbed both the fearlessness and the meticulous engineering discipline. Through the mid-1950s, father and son made progressively deeper dives in the Mediterranean, reaching over 3,000 meters. But they had their eyes on something much bigger. And this is where the story takes a turn that involves the United States Navy, the Cold War, and a trench in the Western Pacific that you and I have already talked about. The Navy was interested in the Trieste for reasons that went beyond pure science. This was the late 1950s. The Cold War was intensifying. Submarines were becoming nuclear-powered, diving deeper, staying submerged longer. The Navy needed to understand the deep ocean, its acoustics, its currents, its terrain, for strategic reasons. They needed to know what happened to materials and equipment at extreme depths. And frankly, there was a prestige element too. The Soviets had launched Sputnik in 1957. The space race was on. Going to the deepest point in the ocean would be a statement. So the Navy purchased the Trieste from the Piccards in 1958 and brought it to the Naval Electronics Laboratory in San Diego, where it was modified for an audacious mission called Project Nekton. The goal was simple to state and almost impossible to achieve. Descend to the bottom of the Challenger Deep, the deepest known point in the world's oceans, nearly 11,000 meters down in the Mariana Trench. Think about what that means for a second. Remember the pressure numbers we talked about earlier. At the bottom of the Challenger Deep, the pressure is roughly 1,100 atmospheres. That's about 16,000 pounds pressing on every square inch. Every square inch. The crucisphere had to hold that back with nothing but the geometry of its shape and the strength of its steel. A sphere is the ideal shape for resisting external pressure because the force is distributed perfectly evenly across the entire surface. There are no corners or edges where stress concentrates. But even so, the tolerances were razor thin. Any flaw in the steel, any imperfection in the machining, any tiny crack, and the sphere would implode faster than the human nervous system could register what was happening. On January 23, 1960, Jacques Piccard and Lieutenant Don Walsh of the United States Navy climbed into the Trieste's crucisphere in the waters above the Mariana Trench. The sphere was so small that Walsh, who was a fairly tall man, had to hunch forward the entire time. They began their descent at 8:23 in the morning, local time, sinking through water that went from tropical blue to twilight gray to absolute black within the first few hundred meters. The descent was slow, about a meter per second, roughly the speed of a leisurely walk. They had hours ahead of them, falling through darkness, watching the depth gauge creep upward, listening to the hull. And here's a detail that I find genuinely chilling. At about 9,000 meters, so they're already deeper than any human has ever been, deeper than Everest is tall. They heard a loud crack, a sharp, sudden bang that echoed through the tiny sphere. They didn't know what it was. They couldn't see the outside of their vessel. They didn't know if the hull was compromised, if the next second would bring a catastrophic implosion. They looked at each other. They checked the instruments. Nothing seemed to be failing. After a tense discussion, they decided to continue the descent. They found out later that the sound was the acrylic window in the entry tunnel, not the main crucisphere, but the access shaft above it, cracking under the pressure. It held. But in that moment, falling through pitch blackness at 9 kilometers deep with a mysterious crack ringing in their ears, they didn't know that. They chose to keep going. That decision took a particular kind of courage that I think is worth sitting with for a moment. This wasn't the courage of a split-second reaction. It was a deliberate, reasoned choice to continue descending into a place that was actively trying to destroy them, with incomplete information about whether their machine was still intact. At 1:06 in the afternoon, after nearly 5 hours of descent, the Trieste touched bottom. The depth gauge read 37,800 feet, later recalculated to approximately 10,916 meters. Jacques Picard looked out through the small porthole and saw something that startled him. The sediment on the bottom had been disturbed by their landing, and as it slowly settled, he saw a flatfish, something resembling a sole or a flounder, lying on the seafloor, looking up at them. A living creature at the deepest point on Earth. Now, there's been some debate among marine biologists about whether what Picard saw was actually a flatfish, or perhaps a sea cucumber or some other organism, because no fish has been confirmed at quite that depth since. But what's not debated is that there was life down there. In the most extreme environment on the planet, in total darkness, under pressure that would liquefy human bone, something was alive and going about its business. They stayed on the bottom for about 20 minutes. That's all. 20 minutes after years of engineering, months of preparation, and 5 hours of descent. They couldn't collect samples. They couldn't do much science. The Trieste had no manipulator arms, no sophisticated cameras. But what they did was prove that it was possible. A human being could travel to the deepest point in the ocean and come back alive. And that proof of concept mattered enormously, even though, and this is a fact that surprises most people, it would be 52 years before anyone went back. 52 years. Think about that. We went to the bottom of the ocean in 1960, and then we went to the moon in 1969, and we kept going back to the moon, and we sent robots to Mars, and we built a space station, and we launched telescopes to the edge of the solar system, and for more than half a century, nobody returned to the deepest point on Earth. The Challenger Deep was lonelier than the lunar surface. Part of the reason is cost, and part is engineering difficulty. But a big part is simply that there was less institutional motivation. Space had geopolitical urgency. The deep ocean had fish, or maybe sea cucumbers. The military applications of deep ocean knowledge were real, but could mostly be served by unmanned instruments and sonar. There was no deep ocean race the way there was a space race, and so the abyss waited. But the deep ocean didn't stop being explored entirely during those decades. Far from it. What happened was that exploration shifted toward unmanned systems and toward shallower but still remarkable depths, and the discoveries that came out of that era reshaped our understanding of life itself. Because in 1977, a team of geologists aboard the research vessel Cunora sent a small towed camera sled down to the Galapagos Rift, a volcanic spreading center on the Pacific seafloor about 2,500 meters deep. And what they found there was so unexpected, so fundamentally weird, that it forced biologists to rethink the basic rules of how ecosystems work. They found hot water, shimmering, mineral-rich water pouring out of cracks in the volcanic rock at temperatures that would scald you in an instant, and clustered around those vents in densities that seemed impossible for the deep sea were animals, enormous animals, tube worms as tall as a person, with bright crimson plumes waving in the current, clams the size of dinner plates, mats of strange white crabs piled on top of each other, mussels clustered so thickly on the rock that you couldn't see the basalt underneath. And all of this life, this riot of biological abundance, existed in total darkness, more than 2 kilometers below the surface, in a place where no sunlight had ever reached. Not once. Not ever. The sun has never touched that rock. And that's what made it so revolutionary. Because up until that moment, every ecosystem we knew about on Earth ultimately depended on the sun. Plants capture sunlight, they photosynthesize, they build sugars, and everything else eats the plants, or eats the things that eat the plants. Even the deep-sea ecosystems we'd already cataloged, the sparse communities of sea cucumbers and brittle stars and weird little fish scattered across the abyssal plains. Even those depended on marine snow, which is just dead surface organisms sinking down. So even the abyss was connected to the sun, just indirectly. The deep ocean floor was, in a sense, living on leftovers from the sunlit world above. But these vent communities were different. These animals weren't waiting for scraps to drift down from above. They were thriving. Not just surviving, thriving, on energy that came from inside the Earth itself. The hot water pouring out of those vents was loaded with chemicals, particularly hydrogen sulfide. And hydrogen sulfide, if you've ever smelled a rotten egg, that's what it smells like. It's toxic to most life. But certain types of bacteria had figured out how to use it the way plants use sunlight. They could take hydrogen sulfide and carbon dioxide and water and run chemical reactions that produced organic molecules, food essentially, without a single photon of light involved. The process is called chemosynthesis, and it's one of the most profound discoveries in the history of biology. An entirely independent energy pathway for life. A second way to build an ecosystem from scratch. Here's what's really clever about how those tube worms work, because they're the poster children of vent ecosystems, and their biology is genuinely strange. Those giant tube worms, the species is called Riftia pachyptila. They don't have a mouth. They don't have a stomach. They don't have a gut at all. As adults, they have no digestive system whatsoever. Instead, they have an organ called a trophosome, which takes up most of their body cavity, and it's packed with billions of chemosynthetic bacteria. The worm basically farms bacteria inside its own body. It uses its bright red plume, that feathery crimson structure, waving at the top of the tube, to absorb hydrogen sulfide and oxygen and carbon dioxide from the water, binds them to specialized hemoglobin in its blood, and delivers those raw materials directly to the bacteria living in its tissues. The bacteria do the chemistry, produce organic carbon, and the worm absorbs the nutrients. It's an internal symbiosis so complete that the worm has literally lost the ability to eat. It doesn't need to. It carries its own food factory everywhere it goes. And that red color, by the way, that's hemoglobin. Same molecule that makes your blood red. These worms have blood that's rich in hemoglobin because they need to transport both oxygen and hydrogen sulfide simultaneously through their circulatory system, which is a neat trick because hydrogen sulfide is normally poisonous to hemoglobin-based blood. In your body, hydrogen sulfide would bind to your hemoglobin and shut down your cellular respiration. You'd die. But Riftia has a modified hemoglobin with separate binding sites for oxygen and sulfide, so it can carry both without them interfering with each other. Evolution solved a chemistry problem that would stump most biochemists. Now, the team that first found these vents in 1977 was actually looking for something else entirely. They were geologists, not biologists. The expedition was led by Jack Corliss from Oregon State University, and they were investigating the Galapagos Rift because temperature anomalies in the water near the spreading ridge suggested that hot water was seeping out of the sea floor. This was predicted by plate tectonics theory. At mid-ocean ridges, where tectonic plates pull apart, new crust forms from upwelling magma, and seawater percolates down through cracks, gets superheated by the magma below, and rises back up. The geology was expected, the biology was not. When the camera sled came back with photographs of those dense animal communities, Corliss reportedly couldn't believe what he was seeing. The images looked like an oasis in the middle of a desert. The following year, in 1979, a team went back with the submersible Alvin, the same Alvin that the Woods Hole Oceanographic Institution had been operating since the mid-1960s, and they got an even closer look, and that's when they found the black smokers. Black smokers are one of the most visually dramatic things on the entire planet. Imagine a chimney made of dark mineral deposits, sometimes standing 10 or 15 meters tall, and from its top, a jet of superheated fluid blasts out at temperatures up to 400 degrees Celsius. 400 degrees. That's hot enough to melt lead. The fluid looks like black smoke because it's loaded with dissolved metals and sulfides that precipitate out the instant they hit the near-freezing ambient seawater, forming these roiling dark plumes. The chimney itself grows over time as minerals deposit around the vent opening, building these tall, craggy, almost Gothic-looking structures. Some of them look like pipe organs. Some look like haunted castles. And the water coming out of them is so hot that it would be steam at the surface. But at 2,500 meters depth, the pressure is about 250 atmospheres, and that keeps the water in its liquid phase, even at temperatures well above its normal boiling point. This is called superheated water, and it exists in a state that you just don't encounter in everyday life. And here's a disturbing little detail for you. The temperature gradient around a black smoker is one of the steepest on Earth. The fluid coming out of the chimney can be 400 degrees Celsius, and the ambient water just a few centimeters away can be 2 degrees Celsius. That's a temperature difference of nearly 400 degrees across less than the width of your hand. If you put your hand near a black smoker, which you obviously wouldn't, but hypothetically, One side of your hand could be getting cooked while the other side was nearly freezing. The shrimp and crabs that live around these vents navigate this gradient constantly. One wrong move, and they're boiled alive. And in fact, you can sometimes see dead animals around the base of black smokers, creatures that got too close and were killed by the heat. The vent communities exist in this incredibly narrow habitable zone, a thin shell of tolerable temperature between the lethal heat of the vent and the crushing cold of the surrounding deep water. Now, you might be thinking, okay, these vents are fascinating, but how long do they last? And that's a great question, because the answer introduces another layer of strangeness. Individual hydrothermal vents are temporary. They might be active for a few decades, maybe a century or two, and then the underlying geology shifts, the plumbing changes, and the vent dies. The hot water stops flowing. And when that happens, the entire ecosystem around it collapses. The bacteria lose their energy source, the tube worms starve, the crabs disperse or die. A thriving community of hundreds of species can go dark in a geological instant. So every vent ecosystem you see is, in a sense, already dying. It's a temporary garden built on a temporary heat source, and the animals that live there have to be able to colonize new vents when they appear, sometimes hundreds of kilometers away along the mid-ocean ridge. How they do this is still not fully understood, and it's one of the active mysteries of deep-sea biology. Riftia tube worms grow astonishingly fast for deep-sea organisms. They can add more than 80 centimeters of tube length per year, making them among the fastest-growing marine invertebrates known. They need to grow fast because their habitat is ephemeral. But to colonize a new vent, their larvae have to somehow travel through the vast, cold, food-poor deep ocean and find another vent. Some researchers think the larvae might ride deep ocean currents along the ridge axis. Others have proposed that they can detect chemical signals in the water, traces of hydrogen sulfide or other vent chemicals, from considerable distances. But the deep ocean is enormous and vents are tiny, and finding one by chemical trail alone seems like finding a candle in a blizzard. It's one of those problems where the more you think about it, the more impressive the solution must be, even though we don't fully know what that solution is yet. The discovery of hydrothermal vents didn't just change marine biology. It changed astrobiology. Because suddenly, you didn't need sunlight for a complex ecosystem. You just needed water, rock, heat, and the right chemistry. And where else in the solar system do you find water and heat together? Jupiter's moon. Europa has a global ocean of liquid water beneath an ice shell, kept liquid by tidal heating from Jupiter's immense gravity. Saturn's moon, Enceladus, is spraying jets of water vapor into space from cracks in its south polar ice, and the Cassini spacecraft detected hydrogen gas and silica nanoparticles in those plumes, both of which are signatures of hydrothermal activity on a rocky seafloor beneath the ice. If Enceladus has hydrothermal vents at the bottom of a subsurface ocean, and if chemosynthesis is a viable way to power an ecosystem without sunlight, then Enceladus might have life. Not might in the vague, hand-wavy sense, might in the specific, mechanistically plausible sense. The chemistry works. The energy source exists. The water is there. The only question is whether biology actually got started, and that's a question we genuinely don't know how to answer without going there and looking. But let's stay on Earth for a moment, because the deep ocean had more surprises in store during the 1980s and 1990s, and some of them were almost as strange as the vents. Because it turns out that hydrothermal vents aren't the only places where chemosynthetic ecosystems exist on the deep sea floor. In 1984, researchers discovered dense communities of tube worms, clams, and bacterial mats on the floor of the Gulf of Mexico, in areas where there were no volcanic vents at all. Instead, what was seeping out of the seafloor was cold, ambient temperature, and it was methane and hydrogen sulfide leaking up from hydrocarbon deposits buried in the sediment. These are called cold seeps, and they support chemosynthetic ecosystems that can last not for decades, but for thousands of years, because the underlying hydrocarbon reservoirs are enormous and long-lived. The tube worms at cold seeps grow much more slowly than their vent cousins. Some of them are estimated to be over 250 years old, making them among the longest-lived animals on Earth. They exist in a kind of slow-motion version of the vent ecosystem, same basic chemistry, same bacterial symbiosis, but stretched out across centuries instead of compressed into decades. And cold seeps introduced another unsettling feature of the deep ocean, one that sounds almost like science fiction. In certain cold seep areas, particularly in the Gulf of Mexico, methane and other hydrocarbons combine with water under the high pressures and low temperatures of the deep sea floor to form a substance called methane hydrate, sometimes called methane ice or fire ice. It's a crystalline solid that looks like dirty ice, and it's flammable. You can literally set it on fire. It's methane molecules trapped inside a cage of water molecules, stable only under specific conditions of cold and pressure. And there are enormous quantities of it. Some estimates suggest that the total amount of carbon locked up in methane hydrates on the world's continental shelves exceeds the carbon in all known coal, oil, and natural gas reserves combined. That's a staggering number. And it sits there, on the ocean floor and in the sediment just below, in a state of conditional stability that makes some scientists very nervous, because if the ocean warms enough, or if the sediment is disturbed enough, those hydrates can dissociate. The ice melts. The methane escapes as gas, and methane is a greenhouse gas roughly 80 times more potent than carbon dioxide over a 20-year timescale. There's a hypothesis, still debated but taken seriously, that massive methane hydrate releases have triggered rapid warming events in Earth's past, including possibly the Paleocene-Eocene thermal maximum about 56 million years ago, when global temperatures spiked by 5 to 8 degrees Celsius in a geologically brief period. The deep ocean floor, in other words, might be sitting on a climate bomb with a very long and very uncertain fuse. But methane hydrates have another strange property that brings us back to the sheer weirdness of deep ocean chemistry. In certain areas of the Gulf of Mexico, methane and other dense brines seep out and pool in depressions on the seafloor, forming what are essentially underwater lakes. Actual lakes on the bottom of the ocean. They have shorelines. They have surfaces that ripple. You can see the boundary between the brine pool and the surrounding seawater because the brine is so much denser. It's saturated with salt and dissolved methane that it settles into low spots and just sits there, like a lake sits in a valley. Submersibles have filmed these brine pools, and the footage is genuinely surreal. You're already underwater, thousands of meters below the surface, and then you come across what looks like a lake with its own beach, and mussels clustered along the shoreline the way mussels cluster on rocks at the seashore. Some of these brine pools are toxic. The methane and hydrogen sulfide concentrations are lethal to most organisms, and fish or crabs that wander into them can be stunned or killed. Researchers have called them the jacuzzis of despair, which is maybe the most evocative name in all of oceanography. And this brings up something worth sitting with for a moment, because it connects to a theme that keeps coming back the deeper we go into this subject. The deep ocean doesn't play by the rules we're used to. The categories we use to organize the world on land, lakes and oceans, hot and cold, living and dead, rock and water, those categories blur and dissolve in the deep. You get lakes inside oceans. You get ice that burns. You get animals with no mouths that farm bacteria inside their own bodies. You get water that's hotter than an oven but doesn't boil. You get ecosystems that run on poison. Every time you think you've found the edges of what's possible, the deep ocean shows you something that pushes those edges further out. And that's part of what makes it so compelling, and honestly, part of what makes it a little unsettling. Because we like to think we understand the rules. We like to think the world operates within a framework we can predict and categorize. And mostly it does. But the deep ocean is a reminder that our framework was built from surface observations, from the thin, bright, warm, low-pressure layer of the planet where we happen to live. And that framework doesn't always hold when you go deeper. Speaking of going deeper, and of things that don't behave the way you'd expect, let's talk about what happens to sound in the deep ocean. Because this is one of those topics that starts out seeming straightforward and then gets progressively stranger the more you learn about it. You know, that sound travels through water. You've probably experienced that if you've ever been swimming and heard someone's muffled voice from underwater. But what you might not know is that sound travels about 4.5 times faster in water than in air, roughly 1,500 meters per second compared to about 340 in air. And in the deep ocean, the speed of sound doesn't stay constant. It changes with temperature, with pressure, and with salinity. And those three variables create a sound speed profile that varies with depth in a way that's genuinely strange. Near the surface, the water is relatively warm, and warmth makes sound travel faster. As you go deeper, the temperature drops, and so does the speed of sound. It keeps dropping and dropping through the thermocline, that zone where temperature plummets, until you reach a point, usually somewhere between about 600 and 1,200 meters deep, depending on where you are in the world, where the speed of sound hits its minimum. Below that point, something interesting happens. The temperature has already bottomed out. It's hovering just above freezing, and it's not going to change much from here on down. But the pressure keeps increasing, and pressure also affects sound speed. So below that minimum point, even though the water is still bitterly cold, the increasing pressure starts pushing the speed of sound back up again. What you end up with is this sort of U-shaped curve. Sound travels fast near the surface because of warmth, slows down in the middle depths, and then speeds up again near the bottom because of pressure. And that minimum point, that trough of the U, is called the SOFAR channel. Stands for sound fixing and ranging. And here's where it gets really interesting. When sound waves travel through a medium where the speed varies, they bend. They always bend toward the region where they travel slowest. That's basic physics. It's the same reason light bends when it enters glass. So, if a sound is generated near that minimum speed layer, the waves that try to angle upward will curve back down because they're entering faster water above, and the waves that try to angle downward will curve back up because they're entering faster water below. The sound gets trapped. It keeps bouncing back and forth around that minimum speed axis, channeled horizontally through the ocean, like sound traveling through a speaking tube. And because water absorbs much less sound energy than air does, especially at low frequencies, sounds in the SOFAR channel can travel enormous distances. We're talking thousands of kilometers. literally across entire ocean basins. This was discovered during World War II, and the story behind it is worth telling. A scientist named Maurice Ewing, and you'll sometimes see his name spelled out as just M. Ewing in old papers, was working at Columbia University and doing research for the U.S. Navy. Ewing was one of those people who seemed to work on everything at once: seismology, oceanography, underwater acoustics, marine geology. He was relentlessly curious and not particularly concerned with staying in his lane. In 1944, Ewing and a colleague named J. Lamar Worzel conducted experiments where they set off small explosive charges underwater and listened for the sound at distant hydrophones. What they found was remarkable. The sound from these explosions could be detected hundreds, even thousands of miles away, as long as the source was near the depth of that sound speed minimum. The Navy immediately saw the potential. They developed a system where downed pilots could drop a small explosive charge into the water, and listening stations on distant shores could pick up the sound and triangulate the pilot's position. That's where the name SOFAR came from. It was a rescue system, a way to find people lost at sea. But here's the thing that's really wild about the SOFAR channel. It doesn't just carry human-made sounds, it carries natural sounds too. And some of the things that have been recorded in the deep ocean's acoustic environment are genuinely unsettling. In 1997, the National Oceanic and Atmospheric Administration, NOAA, was operating a network of hydrophones in the Pacific that had originally been set up by the Navy for submarine detection and later repurposed for scientific research. These hydrophones picked up an ultra-low frequency sound that was one of the loudest ocean sounds ever recorded. They called it the bloop. It rose in frequency over about a minute and was detected on sensors more than 5,000 kilometers apart. For years, nobody could definitively explain it. Some people speculated it could be a massive, undiscovered marine animal, which is a wonderfully creepy thought. The eventual consensus, reached around 2005 or so, was that it was most likely the sound of a large iceberg cracking and scraping against the sea floor. What's called an icequake. But the fact that it took years to figure that out, and that the deep ocean is full of sounds we're still cataloging and identifying, tells you something about how much we don't know about the acoustic landscape down there. And the bloop wasn't even the strangest one. NOAA's hydrophones have picked up a whole catalog of unexplained or unusual sounds over the years. There's one called Julia, recorded in 1999, that sounds eerily like someone whining or moaning. It lasted about 15 seconds and was loud enough to be heard across the entire equatorial Pacific hydrophone array. Again, probably ice-related. There's Upsweep, which has been detected continuously since the hydrophone array was set up in 1991. A series of narrow-band, upsweeping sounds that seem to come from a volcanically active region of the Pacific. It fluctuates seasonally, peaking in spring and fall, and nobody is entirely sure what process generates it. There's Slow Down, a sound that gradually decreases in frequency over about 7 minutes, first recorded in 1997. These sounds have perfectly mundane, probable explanations: ice, volcanic activity, tectonic shifting. But the fact that the deep ocean has this entire acoustic world that we've only been listening to for a few decades, and that it's full of sounds we can't always immediately identify, is one of those facts that sits with you a little uncomfortably when you think about it at night. Now, the SOFAR channel isn't just interesting for mysterious sounds and military applications. It's absolutely critical for marine life, and this brings us to whales. Blue whales and fin whales produce extraordinarily low-frequency calls, some as low as 10 to 20 hertz, which is right at or below the threshold of human hearing. These calls are perfectly tuned to propagate through the SOFAR channel. A blue whale calling in the deep ocean can theoretically be heard by another blue whale hundreds, maybe even thousands of miles away. Think about what that means. Before commercial shipping filled the oceans with noise, a blue whale in the mid-Atlantic could potentially communicate with another blue whale near the coast of Africa. The ocean was, in a sense, a giant telephone network for whales, and the SOFAR channel was the infrastructure. But here's where it gets disturbing. Human noise has dramatically altered this acoustic environment. The cumulative sound from commercial shipping, from sonar, from seismic air guns used in oil and gas exploration, all of this has raised the ambient noise level in the oceans by a staggering amount. Some estimates suggest that low-frequency ambient noise in the ocean has increased by about 32 times, roughly 15 decibels, over the past 50 years. Decibels are logarithmic, so that's not a small increase. It means the effective communication range for large whales has been dramatically reduced. Where a fin whale might once have been heard across an entire ocean basin, now its call might only carry a fraction of that distance before being drowned out by the rumble of container ships. We've essentially shrunk their world. They're still making the same calls, but nobody can hear them as far away. It's like trying to have a conversation in a room where someone keeps turning up the background music. And it's not just communication. There's growing evidence that ocean noise causes direct physiological stress in marine animals. Beaked whales, which are deep-diving species that use echolocation to hunt in the deep scattering layer, are particularly sensitive to military sonar. There have been multiple mass stranding events. The Bahamas in 2000, the Canary Islands in 2002, Greece in 1996, where beaked whales washed ashore dead or dying in the immediate aftermath of naval sonar exercises. Necropsies revealed hemorrhaging around the brain and inner ear, and in some cases, gas bubble lesions in the tissue that looked a lot like decompression sickness. The leading theory is that the sonar so disorients or terrifies these animals that they alter their dive profiles, surfacing too quickly or diving erratically. And the rapid pressure changes cause the equivalent of the bends. So human sound, transmitted through the very acoustic properties that make the deep ocean such an extraordinary medium for communication, is literally killing animals that have evolved over millions of years to depend on that medium. And speaking of the deep scattering layer, that's something worth pausing on, because it connects acoustics to one of the deep ocean's most astonishing biological phenomena. During World War II, Navy sonar operators kept noticing something strange. There seemed to be a false bottom to the ocean. Their sonar would bounce back from what looked like the seafloor, but it was at the wrong depth, too shallow, and it moved. During the day, this phantom bottom sat at around 300 to 500 meters depth. At night, it rose toward the surface. It took a while to figure out what was going on, but eventually, researchers realized that what the sonar was bouncing off wasn't the bottom at all. It was life, an incomprehensibly vast layer of organisms, fish, squid, jellyfish, crustaceans, siphonophores, so densely packed that it reflected sonar signals like a solid surface. This is the deep scattering layer, and what it does every single night is undertake the largest migration on Earth. Every evening, as the sun sets, billions upon billions of organisms rise from the deep twilight zone toward the surface to feed under cover of darkness. Every morning, they descend again, retreating from predators and sunlight back into the cold, dark depths. This vertical migration happens every single day across every ocean, and the total biomass involved is staggering. Some estimates put it at over 10 billion tons of animals moving up and down the water column every 24 hours. 10 billion tons. That's more than the total mass of all the humans on Earth, moving vertically through the ocean every single day, and most people have never heard of it. And here's something about this migration that researchers are only beginning to understand. It plays a significant role in the global carbon cycle. When these animals feed at the surface and then descend to depth, they carry carbon with them in their bodies, in their fecal pellets, in the bits of food they didn't finish digesting. This biological pump, as it's called, actively transports carbon from the surface ocean, where it was fixed by photosynthesis, down into the deep, where it can be sequestered for centuries or millennia. Some of that carbon ends up in the sediment. Some of it gets consumed by deeper-dwelling organisms and enters the deep ocean food web. But the net effect is a downward transport of carbon that helps regulate atmospheric CO2 levels. And the deep scattering layer, with its nightly migration, is one of the engines driving that pump. If something disrupted that migration, widespread ocean noise, changes in oxygen levels at depth, shifts in the food web due to warming, the consequences for global carbon cycling could be profound. And that's not a hypothetical worry. It's something oceanographers are actively tracking right now, because the ocean is already changing in ways that touch every layer of that vertical highway. Let's stay with carbon for a moment, because the numbers are genuinely remarkable. The ocean as a whole absorbs something like a quarter of all the CO2 that humanity pumps into the atmosphere every year. A quarter. That's billions of tons of carbon dioxide that would otherwise be warming the planet even faster than it already is. And a meaningful fraction of that absorption depends on biological processes, not just the physical dissolution of gas into seawater, but the active work of living organisms pulling carbon down. The biological pump, driven in part by that massive daily migration we were just talking about, is estimated to transport somewhere between 2 and 6 billion tons of carbon to the deep ocean annually. The range is wide because it's incredibly hard to measure. You're trying to account for the metabolic output of trillions of organisms scattered across every ocean basin. But even the low end of that estimate is enormous. It's comparable to the total carbon emissions of the United States in a year. And a lot of it hinges on the health and behavior of creatures most people will never see. Tiny lanternfish, bristlemouth fish, copepods, krill, siphonophores, all these animals that make up the deep scattering layer. Here's what's unsettling. The ocean's ability to keep doing this isn't guaranteed. As surface waters warm, they become lighter, more buoyant relative to the cold water below. This increases what oceanographers call stratification. The layering of the ocean becomes more rigid, harder to mix. And when mixing slows down, fewer nutrients get carried up from the deep to the surface, which means less phytoplankton growth, which means less food for the zooplankton and small fish that drive the biological pump. You get this cascading effect, where warming at the surface can starve the engine that pulls carbon into the deep. It's a feedback loop, and it runs in the wrong direction. And there's another piece of this that's even more troubling. As the ocean absorbs more CO2, the water itself becomes more acidic. You've probably heard the term ocean acidification. Since the beginning of the Industrial Revolution, the pH of surface seawater has dropped by about 0.1 units. That might sound trivial, a tenth of a pH unit. But pH is logarithmic, so that represents roughly a 30% increase in hydrogen ion concentration. 30% more acidic in about 250 years. And the rate of change is accelerating. For organisms that build shells or skeletons out of calcium carbonate, things like pteropods, those tiny swimming snails sometimes called sea butterflies, or coccolithophores, the microscopic algae that form chalky plates around themselves. This is existential. Below a certain pH, calcium carbonate literally starts to dissolve. There's a depth in the ocean called the carbonate compensation depth, or CCD, below which no calcium carbonate accumulates on the seafloor because it dissolves faster than it can settle. As the ocean acidifies, that depth is getting shallower. The zone where shell-building organisms can survive is shrinking from below. Pteropods are a good example to linger on, because they're one of those animals that seem insignificant until you realize how much depends on them. They're tiny. Most are smaller than a lentil. They have these delicate, translucent shells, and they swim by flapping two wing-like extensions of their foot, which is why they got the name sea butterfly. They're beautiful, in a fragile, otherworldly way, and they're a critical food source for juvenile salmon, herring, cod, and a whole chain of commercially important fish. In some parts of the Southern Ocean, pteropods are a major component of the diet of fish that feed whales. Researchers have already documented pteropods in the Southern Ocean and the North Pacific whose shells are showing signs of dissolution, pitting, thinning, in some cases holes eaten right through. These aren't projections for the year 2100. This is happening now, in water samples collected in the last decade. So you've got this picture forming. The deep ocean isn't some static, unchanging place insulated from what happens at the surface. It's intimately connected. Carbon dioxide from a power plant in Ohio ends up dissolved in seawater off Antarctica, changing the chemistry that a pteropod in the Southern Ocean depends on, which affects the food web that supports krill, which supports whales, which when they die and sink contribute their own massive pulse of carbon to the deep sea floor in what marine biologists have started calling whale fall. And whale fall, let's talk about that for a second, because it's one of those deep ocean phenomena that is simultaneously macabre and astonishing. When a great whale dies and its carcass sinks to the abyssal plain, it creates an entire ecosystem. A single whale carcass can weigh 30, 40, even 60 tons. It lands on the seafloor, which might otherwise be a vast, nutrient-poor desert of sediment. And suddenly, there's this bonanza of organic material. The first stage is what researchers call the mobile scavenger stage. Hagfish arrive, sometimes dozens of them, burrowing into the flesh. Sleeper sharks cruise in. Amphipods swarm in clouds so thick they look like blizzards in submersible footage. A large whale carcass can sustain this feeding frenzy for months, maybe a year or two, with scavengers consuming an estimated 40 to 60 kilograms of tissue per day. But then something interesting happens. After the soft tissue is mostly gone, you enter what's called the enrichment opportunist stage. The bones and remaining scraps have enriched the surrounding sediment with organic matter, and dense colonies of polychaete worms and crustaceans move in, thriving on the nutrient-rich mud. This stage can last for years. And then comes the truly remarkable phase, the sulfophilic stage. The whale's bones are saturated with lipids, with oils. Whale bones are extraordinarily fatty. It's part of what gives whales their buoyancy in life. And as anaerobic bacteria break down those lipids, they produce hydrogen sulfide, the same chemical that drives hydrothermal vent ecosystems. So the whale skeleton becomes, in effect, a miniature vent system, supporting chemosynthetic bacteria that form the base of a food web, including specialized mussels, clams, limpets, and a worm called Oceanographic, the bone-eating snot flower, which is genuinely its common name. Oceanographic has no mouth, no gut. It sends root-like structures into the bone, and symbiotic bacteria inside those roots break down the bone lipids for energy. This sulfophilic stage can persist for 50 to 75 years on a single whale skeleton. One dead whale, sustaining a unique community for the better part of a century. Craig Smith at the University of Hawaii was one of the first researchers to systematically study whale falls, starting in the late 1980s and into the 1990s. His team discovered that whale falls support species found nowhere else, obligate whale fall specialists that depend entirely on this habitat. And here's a thought that's both elegant and a little haunting. Before commercial whaling, when great whale populations were perhaps 10 times larger than they are today, whale carcasses on the deep sea floor would have been far more common. The average distance between whale falls might have been only 10 or 20 kilometers in some ocean basins. That's close enough for the larvae of whale fall specialists to drift from one carcass to the next, maintaining connected populations. Some researchers have speculated that whale falls may have served as stepping stones between hydrothermal vents and cold seeps, allowing chemosynthesis-dependent species to colonize across ocean basins. Whaling, by dramatically reducing whale populations, may have increased the distances between whale falls to the point where some of these specialist species lost connectivity between populations. We may have driven deep-sea species toward extinction without ever knowing they existed, simply by removing the whales whose deaths sustained them. That idea sits with you, doesn't it? The notion that the ecological consequences of whaling extend not just to the whales themselves, not just to the surface ocean food web, but down to the abyssal plain, to organisms living on whale bones in total darkness 3,000 meters below the surface. It's a reminder of how deeply interconnected these systems are, how an action at the surface ripples downward in ways nobody anticipated. And this brings us to something that's increasingly on the minds of marine scientists and policymakers alike, the question of what we're about to do to the deep sea floor deliberately. Because there's an industry taking shape right now, one that's been talked about for decades, but is only now approaching operational reality, and it has the potential to disturb the deep ocean on a scale that makes everything else we've discussed look modest. It's called deep sea mining, and the story of how we got here starts, oddly enough, with a 19th century oceanographic expedition we've already talked about, the Challenger expedition. Because when John Murray and his colleagues were cataloging all those samples they'd dredged up from the deep sea floor in the 1870s, they kept finding these strange, dark, potato-sized lumps scattered across the abyssal sediment. Murray described them carefully. They were rounded, sometimes nodular, sometimes more like a flattened disc, and when you cracked one open, you found concentric layers of metal oxides built up around a central nucleus. Maybe a shark tooth, maybe a fragment of bone, maybe just a tiny piece of rock. They were rich in manganese and iron, but also contained meaningful amounts of nickel, copper, and cobalt. Murray recognized they were interesting, but in the 1880s, nobody had any practical use for lumps of metal sitting 4,000 or 5,000 meters below the ocean surface. So he documented them, published his findings, and the scientific world mostly moved on. For about 80 years, polymetallic nodules, that's what we call them now, were a curiosity, a footnote in oceanographic textbooks. Then, in the 1960s, a geologist named John Marrow published a book that changed everything. It was called The Mineral Resources of the Sea, and Marrow laid out an argument that was, frankly, astonishing. He estimated that the Pacific Ocean floor alone contained something like 1.5 trillion tons of these manganese nodules. Trillion with a T. And they weren't just manganese. They contained enough nickel, copper, and cobalt to supply global demand for thousands of years. Merrow painted a picture of essentially limitless mineral wealth just sitting on the ocean floor, waiting to be scooped up. And here's the detail that really captured people's imagination. The nodules grow. They accrete new layers of metal from dissolved minerals in seawater, adding material at a rate of maybe 5 to 20 millimeters per million years. That's extraordinarily slow. We're talking geological timescales, but Merrow suggested, somewhat optimistically, that the ocean was producing new nodules faster than we could ever harvest them. A self-renewing resource. Now, you have to understand the context. This is the 1960s. The Cold War is in full swing, and both the United States and the Soviet Union are hungry for strategic metals. Cobalt, nickel, manganese, these are critical for steel alloys, for jet engines, for military hardware. And the land-based sources of these metals are concentrated in politically unstable regions, particularly Central Africa. The idea that you could bypass all of that geopolitical complexity by simply vacuuming up nodules from the ocean floor was incredibly appealing. Mining companies started paying attention. Governments started funding research. By the early 70s, several major consortia had formed, groups like Kennecott, Lockheed, and various Japanese and European firms, all racing to develop the technology to harvest nodules from the abyssal plains, and they actually built prototype systems. The basic concept isn't that complicated in principle, even if the engineering is nightmarish in practice. You lower a collector, essentially a giant vacuum head, down to the seafloor on a riser pipe. You suck up nodules along with the surrounding sediment, separate the nodules from the mud, pump them up to a surface vessel, and process them. Lockheed's subsidiary, Ocean Minerals Company, actually tested a pilot system in the Pacific in the late 70s and successfully brought nodules up from over 5,000 meters. It worked. It was expensive and clunky, but it worked. Then something interesting happened. Metal prices dropped. The global economy shifted. The immediate strategic urgency faded, and the whole enterprise quietly stalled. By the mid-1980s, deep-sea mining had retreated back into the realm of future possibility, a technology waiting for its economic moment. But here's the thing. The legal and political machinery kept grinding forward even after the industry lost interest. Because the prospect of deep-sea mining had raised a genuinely profound question. Who owns the bottom of the ocean? The nodules sitting on the abyssal plain aren't in any country's territorial waters. They're in international waters, in what's legally called the area, the seabed beyond national jurisdiction. And in 1967, a Maltese ambassador named Arvid Pardo stood before the United Nations General Assembly and made an argument that still echoes today. He proposed that the mineral resources of the deep seabed should be considered the common heritage of mankind, not first come, first served, not the property of whoever had the technology to grab them. A shared inheritance belonging to every nation on Earth, including landlocked countries, including developing nations that would never build their own deep-sea mining fleet. Pardo's speech helped catalyze the negotiations that eventually produced the United Nations Convention on the Law of the Sea, UNCLOS, which was adopted in 1982 after nearly a decade of talks. UNCLOS created the International Seabed Authority, the ISA, headquartered in Kingston, Jamaica, and gave it the mandate to regulate all mineral extraction in the area. The ISA would issue exploration contracts, set environmental standards, and ensure that the benefits of deep-sea mining were shared equitably. It was an extraordinary piece of international governance, an attempt to manage a commons before it was exploited rather than after, preventive rather than reactive. For years, the ISA mostly issued exploration contracts and waited. Companies and state-sponsored entities would survey patches of the abyssal plain, map the nodule fields, study the biology, and file reports. no actual mining took place. The regulatory framework for exploitation, the rules governing actual commercial extraction, remained unfinished. There was no rush, because nobody was ready to mine anyway. And then the world changed again. This time, it was batteries. The explosive growth of electric vehicles, renewable energy storage, and consumer electronics created enormous new demand for exactly the metals that polymetallic nodules contain: cobalt, nickel, manganese, copper. These are the elements that make lithium-ion batteries work. And suddenly, the economics that had killed deep-sea mining in the 80s started looking very different. Cobalt prices spiked. Nickel demand projections soared. And a significant fraction of the world's cobalt was still coming from the Democratic Republic of Congo, where artisanal mining operations often involved child labor and appalling working conditions. Deep-sea mining advocates began making a new argument. Maybe harvesting nodules from the uninhabited abyssal plain was actually the more ethical option compared to what was happening on land. The company that pushed hardest was called the Metals Company, formerly known as Deep Green, led by a Canadian entrepreneur named Gerard Barron. Barron was charismatic, media-savvy, and relentless in his messaging. He framed deep-sea mining as a climate solution, the metals needed for the energy transition, sourced with a smaller terrestrial footprint than conventional mining. No forests cleared, no communities displaced, no toxic tailings ponds. Just nodules sitting on the seafloor, waiting. But here's where it gets complicated and where the marine scientists started raising alarms, because those abyssal plains aren't empty. They look barren, vast expanses of soft sediment stretching to the horizon, dimly lit by the occasional bioluminescent flash. But they support life. Sparse life, yes. Slow life, certainly. But life that is exquisitely adapted to one of the most stable environments on Earth. The abyssal plain changes almost imperceptibly over millennia. The organisms that live there, tiny polychaete worms, isopods, nematodes, xenophyophores, which are single-celled organisms that can grow to the size of your fist. They've evolved for constancy. They reproduce slowly. They grow slowly. Their populations recover from disturbance slowly, if they recover at all, and the nodules themselves are habitat. Remember, these things have been sitting on the seafloor for millions of years, accreting layer by layer. Their surfaces are colonized by sponges, by corals, by bacterial mats. Many of the species found on and around nodules are found nowhere else. They're endemic to these nodule fields. Studies of the Clarion-Clipperton Zone, a vast stretch of the Central Pacific between Hawaii and Mexico that contains the densest known nodule deposits, have found that something like 70 to 90% of the species collected there are new to science. We're talking about an ecosystem we've barely begun to catalog, let alone understand. Now imagine a collector vehicle the size of a combine harvester, rolling across that seafloor, scraping up the top 10 to 15 centimeters of sediment, ingesting every nodule, and creating a plume of fine suspended particles that drifts for kilometers. The nodules don't come back, not on any human timescale. Remember that growth rate? 5 to 20 millimeters per million years. Once you remove a nodule, it's gone for all practical purposes. And the sediment plume, that's what worries a lot of researchers most. Abyssal organisms are adapted to almost zero turbidity. Suddenly blanketing them in resettled sediment could smother filter feeders, clog respiratory structures, and bury food sources. Some modeling studies suggest that sediment plumes from mining operations could spread hundreds of kilometers from the extraction site, affecting vastly more area than the mining footprint itself. There's also the midwater column to think about. Most proposed mining systems would pump a slurry of sediment and water up to the surface vessel, extract the nodules, and then discharge the wastewater back into the ocean at some intermediate depth, maybe 1,000 or 1,500 meters down. That discharge plume would introduce sediment, dissolved metals, and altered water chemistry into the mesopelagic zone, right in the heart of that deep scattering layer we talked about earlier, where all those lanternfish and shrimp and squid are conducting their nightly vertical migration. The potential for disruption to the biological carbon pump, to mid-water food webs, to the organisms that connect the surface ocean to the deep, it's genuinely unknown, and that uncertainty is itself a kind of warning. In June of 2023, the ISA met in Kingston under unusual pressure. The Pacific island nation of Nauru had triggered an obscure provision in UNCLOS 2 years earlier, essentially forcing the ISA to either finalize its mining regulations or begin accepting mining applications under whatever rules existed. It was a legal maneuver sponsored in effect by the Metals Company, which held exploration rights through Nauru's sponsorship. The move was controversial. Many nations, including France, Germany, and a growing coalition of Pacific Island states, called for a moratorium or a precautionary pause on mining until more science could be done. Environmental organizations mobilized. Even some of the companies that would eventually need the metals, BMW, Volvo, Samsung, signed pledges to avoid using deep-sea mined minerals in their supply chains, at least for now. As of the most recent sessions, the ISA still hasn't finalized the exploitation code. The debate continues. And it's a genuinely difficult one because both sides are making arguments grounded in real concerns. The energy transition does require enormous quantities of critical minerals. Land-based mining does cause tremendous environmental and social harm. But the deep ocean is the largest habitat on Earth, and we understand so little of it that we can't even properly assess what we'd be risking. It's the tension between two kinds of precaution: the precaution of protecting a barely known ecosystem, and the precaution of not delaying the clean energy transition that the planet desperately needs. And it's not just nodules. There are two other types of deep-sea mineral deposits that mining interests have their eyes on. Seafloor massive sulfides. Those are the mineral-rich deposits formed at hydrothermal vents, the same vents where we discovered chemosynthetic life in 1977. Mining those would mean directly disturbing some of the most biologically extraordinary habitats on the planet. And then there are cobalt-rich ferromanganese crusts, which form on the flanks of seamounts, underwater mountains that rise from the abyssal plain and serve as oases of biodiversity in the deep ocean, concentrating currents and nutrients and supporting dense communities of deep-water corals and sponges. Each of these deposit types presents its own engineering challenges and its own ecological risks, and the conversations around them are still evolving, still unresolved, and in some ways even more fraught than the nodule question. Because at least with polymetallic nodules, you're talking about an abyssal plain, a vast, quiet, slow-moving environment. With seafloor massive sulfides, you're talking about going back to those hydrothermal vents, those incredible oases we spent so much time marveling at earlier, and essentially dismantling them for their mineral wealth. The sulfide deposits form over thousands of years as superheated, mineral-laden water erupts from the seafloor, and the dissolved metals precipitate out when they hit the near-freezing seawater. Copper, zinc, gold, silver, they're all there, concentrated in chimneys and mounds that can be tens of meters tall and hundreds of meters across. From a purely geological perspective, they're remarkably richer bodies. Some sulfide deposits contain copper grades several times higher than what you'd find in a typical land-based copper mine. And copper, of course, is one of those metals the energy transition absolutely cannot do without. Every wind turbine, every electric vehicle, every solar panel, every meter of upgraded electrical grid requires copper. So the temptation is real. But think about what mining those deposits would actually involve. You'd be sending heavy machinery to the seafloor to grind up the chimneys and mounds, slurry the material, and pump it to the surface. And in doing so, you'd be obliterating the very structures that support those extraordinary chemosynthetic communities, the tube worms, the vent shrimp, the microbial mats, the whole intricate web of life that exists nowhere else on Earth. Now, proponents of sulfide mining point out something interesting. Hydrothermal vents are naturally ephemeral. Individual vents can go dormant or shift location as the underlying volcanic plumbing changes. The organisms that live at vents have evolved to cope with this instability. They're colonizers, dispersers, adapted to finding new vents when old ones die. So the argument goes that if you mine an active vent, life will eventually recolonize it, or colonize a new vent nearby. And there's some truth to that. Vent communities can reestablish themselves on surprisingly short timescales, years to decades rather than centuries. But here's the thing. There's a big difference between a vent naturally going dormant, with its mineral structures still largely intact and new vents opening nearby along the same ridge system, and a mining operation that physically removes the substrate, the chimneys, the mounds, the sulfide rock itself. If you take away the rock, you take away the surface that organisms settle on. You take away the porous architecture that channels fluid flow. You change the game in ways that natural dormancy doesn't. And we still don't fully understand the connectivity between vent populations, how larvae get from one vent field to another, how genetically distinct different vent communities are, whether losing one field could sever a critical link in the chain. Remember those questions about larval dispersal we touched on earlier? They matter enormously here, and we still don't have definitive answers for most vent species. There's also the question of whether mining would target active vents or inactive ones. Inactive sulfide deposits, places where the venting has stopped but the mineral mounds remain, are actually more attractive from a mining standpoint in some ways. The deposits are cooler, more stable, easier to work with. And since there's no active venting, you don't have the dense chemosynthetic communities. So it sounds like a cleaner option. But inactive sulfides aren't biological deserts either. They support their own communities, different from active vent fauna, but still poorly understood. Sponges, corals, and other filter feeders colonize the hard substrate of old sulfide mounds, and inactive deposits are far more numerous and widespread than active ones, so mining them at scale could affect a much larger total area of seafloor. The cobalt-rich crusts on seamounts present yet another set of complications. Seamounts are fascinating features. There are estimated to be over 100,000 of them in the world ocean, though only a small fraction have been surveyed in any detail. They rise from the deep seafloor, sometimes reaching within a few hundred meters of the surface, and they interact with ocean currents in ways that concentrate nutrients and create hotspots of biological activity. Deep water corals grow on their flanks, not the reef-building corals you picture in tropical shallows, but cold water species that grow incredibly slowly, sometimes just a few millimeters per year. A single coral colony on a seamount might be hundreds or even thousands of years old. The ferromanganese crusts that coat seamount rocks are similarly ancient. They accumulate at rates of just a few millimeters per million years, making them among the slowest growing geological deposits on Earth. They're rich in cobalt, which is critical for the cathodes in many lithium-ion battery designs, and they contain other valuable metals like tellurium and rare earth elements. But harvesting those crusts would mean scraping the surface of the seamount, essentially skinning it. And that surface is where the corals and sponges live, where fish aggregate, where the biological community has its foundation. Recovery timescales for seamount ecosystems, after that kind of disturbance, would be measured not in years or decades, but in centuries or millennia, if recovery is even possible in any meaningful sense. Some researchers have described seamount fauna as functionally non-renewable on human timescales. So you can see how the deep-sea mining debate isn't one debate. It's at least three, each with different ecosystems at stake, different mineral targets, different engineering requirements, and different risk profiles. And all of them are unfolding against the backdrop of that fundamental tension we talked about, the need for minerals versus the imperative to protect what we barely understand. Let's step back from mining for a moment, though, because there's something larger worth sitting with as we wind down tonight. And it's this: the deep ocean, in all its strangeness and darkness and pressure and silence, is not separate from the world you live in. It's not a distant abstraction. It's intimately connected to the air you're breathing right now, to the climate that shapes your days, to the food webs that sustain billions of people, to the very chemistry of the planet's surface. We talked about the biological carbon pump, how the deep ocean sequesters carbon and regulates atmospheric CO2. We talked about how the ocean has absorbed roughly a quarter of the carbon dioxide humanity has released, and how that absorption is changing the water's chemistry in ways that ripple through ecosystems. We talked about sound, how the ocean carries it across entire basins, how whales have used the SOFAR channel for millions of years, and how we've filled that channel with noise in just a few decades. All of these threads connect. The deep scattering layer, that massive community of organisms migrating vertically every single day, the largest migration on Earth, is simultaneously a critical part of the carbon pump, a key link in marine food webs, and a potential casualty of both mining sediment plumes and ocean warming. Acidification threatens the pteropods and coccolithophores whose shells help ballast sinking particles, which means it threatens the efficiency of carbon export to the deep, which means it could create a feedback loop where less carbon gets sequestered, which means more warming, which means more stratification, which means less nutrient mixing, which means changes in productivity at the surface. It's all one system. The deep ocean isn't the bottom of the world, it's the engine room. And here's what I keep coming back to. We have mapped more of the surface of Mars than we have of our own ocean floor. That's not a metaphor. It's literally true. As of the most recent estimates, something like a quarter of the global seabed has been mapped at modern high-resolution standards. The rest is still known only from satellite-derived gravity measurements, which can detect large features like seamounts and trenches, but miss everything smaller. We know more about the topography of the Moon, of Venus, than we do about what lies beneath the waves on our own planet. Think about what that means. Every time a remotely operated vehicle descends to an unexplored patch of deep sea floor, there's a genuine chance it will find something no human has ever seen. New species, not just new species, but sometimes new genera, new families, organisms so different from anything known that they force us to rethink our categories. In the Clarion-Clipperton Zone alone, the area most targeted for nodule mining, surveys have consistently found that the majority of species collected are new to science, 70 to 90% depending on the study. We are talking about mining an ecosystem where we haven't even named most of the residents. And it's not just taxonomy. The deep ocean keeps revealing biological strategies that challenge our assumptions about what life can do. Organisms that thrive at pressures that would crush engineered steel. Microbes that metabolize iron, manganese, sulfur, hydrogen, methane, extracting energy from reactions so subtle that for decades we didn't believe they could sustain life. Fish that see with eyes adapted to detect bioluminescent flashes in absolute darkness. Jellyfish that are functionally immortal, reverting to juvenile stages when stressed. The deep ocean is, in a very real sense, the last great frontier of biological discovery on Earth. And maybe that's a comforting thought to settle into as you drift off tonight. Not the disturbing facts, though we've certainly covered plenty of those, but the sheer scale of what remains unknown. There's something almost restful about it, isn't there? The idea that the planet still holds mysteries so deep, so vast, so fundamentally beyond our current understanding, that entire careers can be spent exploring a single seamount, a single vent field, a single abyssal plain, and still barely scratch the surface. The deep ocean doesn't care about our timelines or our debates. It just continues, dark, cold, patient, immense. The pressure at the bottom of the Mariana Trench is the same tonight as it was when the Trieste touched down in 1960. The vents are still venting. The marine snow is still falling. That quiet, endless rain of organic particles drifting down through the water column, taking weeks to reach the bottom, carrying carbon from the sunlit world into the darkness below. Somewhere right now, a whale fall is in year 30 of its slow decomposition, its bones colonized by Osedax worms and sulfophilic bacteria, a tiny island of abundance on the vast abyssal plain. Somewhere, a pod of sperm whales is diving to 1,000 meters, hunting squid in the blackness, their clicks echoing through water that hasn't seen sunlight in its entire existence. The ocean covers more than 70% of the Earth's surface, and its average depth is about 3,700 meters. That's an almost incomprehensible volume of water, of darkness, of life. And most of it, the honest truth is that most of it remains unexplored, unmapped, unknown. We've sent 12 people to the surface of the moon. Only 3 people have been to the bottom of the Challenger Deep. The deep ocean is right here, beneath the waves, beneath the ships, beneath the storms, and it is still, in the most fundamental sense, terra incognita. Or perhaps we should say aqua incognita. So as you lie there tonight, wherever you are, whatever the hour, just hold that thought gently. Beneath the surface of the world you know, the world of sunlight and air and solid ground, there is another world, one that is older, darker, stranger, and more vast than almost anything else on this planet. It has been there since before there were eyes to see it. It will be there long after our debates about mining codes and carbon budgets are settled one way or another. The deep ocean is patient. It keeps its secrets on its own schedule. And tonight, as you let your breathing slow and your thoughts soften and the weight of the day ease off your shoulders, you can let that vastness be a kind of comfort. You don't have to understand it all. Nobody does. Not yet. Maybe not ever. And that's okay. The ocean doesn't ask to be understood. It just asks to be there, deep, dark, quiet, and full of wonders we haven't even begun to imagine. Let that carry you down now, gently, like marine snow falling through still water, drifting slowly, softly, all the way to the bottom of a good night's sleep.